So we're here again with another problem, and what we're going to look at now is, just give me just one moment. Okay, another problem we're going to look at now is elimination game. So I haven't seen this question yet, so this is like out the gate. How do we do? How does this go? It's new to me. Have a list array of all integers in the range 1 to n sorted in a strictly increasing order. Apply the following algorithm on array. Starting from left to right, remove the first number and every other number afterward until you reach the end of the list. So left to right, first number and every other number afterward until you reach the end of the list. Okay. Repeat the previous step again, but this time from right to left. Remove the rightmost number and every other number from the remaining numbers. Keep repeating the steps again, alternating left to right and right to left until a single number remains. Given the integer n, return the last number that remains in array. So n equals 9, output 6. 1, 3, 5, 7, 9 get removed. 8, 4 get removed. And then 2 gets removed, you're left with 6. So this is an interesting question, and n is going to be between 1 and 10 to the 9th. Okay, so a few things to say about this. This is an interesting question. Yeah, I guess it's an interesting question. Also, the number of steps, because you're removing roughly half at each point, at each execution, this is going to be a logarithmic number of steps, right? Which is great. It's not that many. And then on top of it, though, you've got n. If you actually perform this removal, excuse me, let's say you had a linked list, which has efficient removal, or even just an unordered set, hash set of these numbers that also has efficient removal. Although it's a little harder if you had a doubly linked list, this may be easier. So if you put this into a doubly linked list, you could do it in n log n time, where it takes you O of n time at each step. Now what's interesting about that, it takes O of n time at each step. However, each step, it's not really O of n because you're doing half as much at each step, right? So you're doing something that looks like this. You're doing n plus n over 2 plus n over 4 plus n over 8 ... plus 1, right? Which basically gives you n of 1 plus a half plus a fourth plus ... This is sort of, this is like, really this is n over 2 raised to the log n, something like that. And this is 1. So this ends up being O of n time, believe it or not. So actually, if you did this efficiently with a doubly linked list, this would take O of n time. However, this is a billion. 10 to the 9th, I think, is even more than a billion. Yeah, it's 10 figures, right? Yeah, 10 to the 9th, 10 figures. So that's a billion. That's a lot of work, even if it's linear time. So we've got to find something that's more efficient than that. So it's got to be either logarithmic or better, our counting problem, our solution. And let's try some small examples to get an idea what's going on, possibly what's going on here. So 1, 2, 3, 4, 5. So the one that they had was 9. We'll try that one too. So first step, we say 3, 5. Second step, we do 4, and then we're done. We have 2. Okay, how about 1, 2, 3, 4, 5, 6. First step, 1, 3, 5. Second step, 6, 2, and 4. So n is 5, we get 2. N is 6, we get 4. Okay. Interesting. See if we notice any patterns or anything useful or meaningful, something that we can possibly use. So left to right, and 6, 2. Same kind of deal. Interesting. So 4 is the same. N equals 7, you get 4. Okay, not really a pattern, but getting close to a possible pattern, maybe. I don't know. 1, 2, 3, 4, 5, 6, 7, 8. 1, 3, 5, 7. 8, 4, 2. I did it wrong, didn't I? Yeah, I did it wrong. I'm sorry. Let me go all the way back. I did this wrong. Let's go to 6. One, 2, 3, 4, 5, 6. It's every other one, right? So 1, 3, 5. And then we do 6. Skip 4, 2. So 4. 1, 2, 3, 4, 5, 6, 7. 1, 3, 5, 7. 6, skip 4, 2. Okay, 4 again. 1, 2, 3, 4, 5, 6, 7, 8. I redid the other ones because I wasn't sure if I made the same mistake on the other ones, and I thought it's easier to just do it again instead of trying to retrace my steps. 1, 3, 5, 7. 8, skip 6, 4, skip 2. 2, leave 6. Okay. Interesting. Seeing something of a pattern here. Pattern emerging. 9, I think we get the same thing. 1, 2, 3, 4, 5, 6, 7, 8, 9. I think we already said 9 was 6, but let's try it. 1, 2, 3, 4, 5. Now again, what's really interesting about this is because it's logarithmic, there really are not that many steps that are going to happen. So in theory, we kind of should see this pattern emerge kind of quickly. 8, skip 6, 4, skip 2. Left side we take out 2, left with 6. What about n equals 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I can already make a guess that this is going to be 8, but I don't know if it's going to be 8 or not. Let's do it this way. 1, 2, 3, 4, 5. From the right side, 1, skip, 2, skip, skip. Left side, 5, 8. Oh, look at that. How did I know? How did I know that? And I think 11 is going to be 8 as well. Let's see. So right side, 1 every other. And the left, from the other side, every other. And then from the other side, every other. Oh, there is no other. Just 8, okay. And I think n equals 12, you're going to get 9. Again, you're starting to see a pattern. We can kind of guess why this pattern might be. 1, 2, 3, 4, 5, 6. Other side. Oh no. Oh no, not 10. Oh no, it's not 9. I'm sorry, not 9. 10 it's supposed to be. That's my mistake. I don't know why I said 9. It's not the pattern, right? So the pattern seems to be add 2 every 2. So 8 to 9, 8, 9 is going to be 6, and then 10, 11 is going to be add 2, 8, and then 12, 13 would be 10. Right? That seems to be the pattern. Yeah. So you're supposed to skip 1. So 12, we get 8, skip 6, take 4, skip 2. On the other side we say 2, skip 6. Oh, wait. Oh no. 10. Oh no. Uh-oh. Uh-oh. Alright, well, I'm wrong. It's not 10. 6 is not 10. 12 is not 10, it's 6. So there goes my theory. What did I say? This is 6? What do we get for 12? Correct in both cases, really. Yeah, alright. Uh-oh. So my guess is wrong. Okay. Let's get rid of this. We don't need to do this analysis anymore. We don't even need this part. Okay, so okay, so we keep going. 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I don't quite have an idea of what the pattern is yet. Okay. 1, 2, 3, so 7, 9, 11, 13, 12, 8, 4, 2, skip 6, 10, and I think it's just 6 again. Huh, how does that happen? I want to go more. I want to go further ahead. I want to know. I want to know. I want to know. You know, there's a more efficient way to do this too, by the way, which is, if I'm going to do this, we could write a script that actually simulates this and gives us an idea. Although I don't like implementing doubly linked lists, so I don't want to write a script. It's my excuse. It's my reason. My reason for going into such detail, doing it by hand. 13 minutes going it by hand. It's like I don't really like messing around with doubly linked lists. It's kind of a nuisance. Don't like doing a lot of things. That's one of them. It's one of them. Doubly linked lists are kind of annoying. Alright. Can we predict this one and why? What kind of, I don't know what pattern we're starting to see here. I don't really see much of a pattern, quite frankly. I don't really know. 2, 4, 4, 6, 6, 8, 8, 6, 6, 8. I guess it'll be 8 again. So we're going to remove half. We'll be left with the even numbers only, right? 2, 4, 6, 8, 10, 12, etc. So it's as if we multiplied all the numbers by 2 and then removed the rightmost half, right? And then repeated the same routine. And then from right to left, that's the even numbers. So we have the even numbers. Now we go right to left, and what do we get? Well, that would be all of the odd numbers, wouldn't it? Not necessarily. Yeah. Well, kind of depends on what's on the right side. Because we always know 1 is on the left side. It's always odd from left to right, but what number it sort of alternates depending on what n is. But it sort of doesn't matter, right? So if we just fix n, so if n is 15 in this case, now it's all the odd numbers. However, we've already removed all the odd numbers, so it's every other even number, I suppose. So now we can't just multiply by 2, can we? Every other even number disappears. And we end up with, what is every other even number though? 2, 4, 6, let's see. Let's do it. Move all the odd numbers. That's simple enough. Now we're going to remove every even number, every other even number. And those even numbers are kind of special because those are an odd times an even. Right? 2 times 1, 2 times 3, right? 2 times 5. So these are even numbers times other even numbers, I guess. Right, this is 2 times 5, 2 times 7, etc. And then there's one more stage of things where we get rid of every other one of those. So end up with 8 again. Okay. Oh, okay. Right. Uh-huh. I don't know, man. Because these even numbers, and then we remove some of those even numbers. Now we're left with I guess they're multiples of 4 in that case. So remove all the odd numbers, right? Then remove all the numbers that are every other even number, which are basically 2 times an odd number. So remove all the odd numbers, then remove 2 times the odd numbers. And now you've got multiples of 4. And then you're going to remove from left to right 4 times the odd numbers, really. Yeah. So each level kind of looks like something like this. I don't know. It's definitely an interesting question. Just looking for patterns here. So odd, remove 1, 3, 5, 7, ... Then remove 2 times the odd numbers, which is 2, 1, 3, 5, 7, ... Right? These are the even numbers. Excuse me. 2, 6, yeah. And then remove 4 times the odd numbers. Right, this is 4, 12, etc. Then I think we're going to remove 8 times the odd numbers. And it looks like we could do this in logarithmic time then. Probably do this in logarithmic time. Oh, excuse me. Because each time we can figure out, I guess each time we can figure out how many of these numbers are, I don't know, I'm not really sure. I mean, I guess what I'm trying to say is we could probably execute each of these steps without determine the end result of each of these steps without actually executing them, if that makes sense. Like we can sort of determine what's left over, I suppose. I don't know. I don't know. I don't know. Yeah, it's really interesting. This is like a really interesting question. There is kind of like sort of an inductive hypothesis where once you remove all the odd numbers, you know that all these numbers are multiples of 2. And then if you remove all the odd numbers that are also multiples of 2, or the 2 times some odd number, remove all those, then you're guaranteed that everything has to be a multiple of 4. And then you can remove all the things that are 4 times an odd number, and then it guarantees everything's a multiple of 8, and so on. And you can see how very quickly this is logarithmic, right? Really interesting question. I like this question a lot. It's awesome. Excuse me. Really, it's how many executions do you do before you end up with one element left? And then you can figure out what that element's a multiple of. Is that element a multiple of 8 or 6? N equals 12, right? Am I wrong with this? I think it might be. I don't know. It's also, it could be the other way around too. Right. The second step kind of changes depending on what you're doing. 2, 6, 10. It's not necessarily 2, 6, 10. In this case, it was when it's the even case, it's 2, 6, 10. When it's the odd case, looks like it's also 2, 6, 10. Some cases it's 4, 8, 12. Yeah. Just different from 2, 6, 10. Oh. So not always. So this isn't totally correct. What we're looking at here. It's not completely correct. Excuse me. This is such a weird question. Very interesting. Very strange. Got my my noggin to jog in here. Definitely more maths kind of a question. Huh. Ooh, excuse me. We could think about another data point here. We have n equals 16. Let's try that. So 1, 2, dot, 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 16. Get rid of all the odd numbers. Then get rid of every other even number. Yeah, it's every other one, right? So 4, get rid of 4, get rid of 8, get rid of 12. I think we, wait a second, 2, 4, 6, 8, 10, 12, 14, 16. It actually goes the other way around. Excuse me. Yeah, so we get rid of the odd numbers, go left to right. When we get rid of the even numbers, we go right to left. And that'll be like so. Which will give us 2, 6, 10, 14. Yeah, that's a little strange, huh? I know we're left with 4 numbers, but dude, this is so weird. I end up with 6 again. Why do I feel as though it's always going to be between, it's going to be 2, 4, 6, 8, 2, 4, 6, and 8. Feels like it's always going to be some variation of these things. I think it's, I want to say it's going to be bounded by some logarithmic amount, you know, like, excuse me, if you had 1,000 numbers, what would be left, right? I don't know. You have 500 numbers and they'd all be even numbers. And then, so this one is 6. N equals 16 is 6. Why though? I guess depending on whether it's even or odd, this number, that'll tell you whether or not you have 2, 6, 10, 14, or, you know, 4, 8, I guess, 4, 8, 12, etc. Right? Kind of lets you know one or the other. If this is n is modulo 2 or not. If n is divisible by 2 or not. 2 divides n, we'll say. And then, right, you get a choice between these two. And then, if you have a choice between those two, I think this ends up being 16 here. By the way, I don't think this is a dot, 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 but it would be kind of a dot, dot, dot. I guess that'd be like 17. So if 2 divides n, you end up with this guy, 2 at the front. And then the next decision is, you know, if this was 4, 8, 12, 16, right? Let's say you got rid of 17. Then you're going to go left to right, 4, 12. Now you have 8, 16, probably 24, dot, 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 right? This is going to be 2 to the 3rd. This is going to be 2 to the 4th, or squared. Multiples of 2 squared, multiples of 2 to the 3rd, and this is going to be it looks like 2 to the 3rd minus 2. 6, 14, 22. So they seem like the same sequence you're going to get, it's just one of them is decremented by 2. And then here, if your sequence is 6, 14, and you only have one number left, and it seems like, Right, each power of 2, you're gonna sort of reduce further and further, right? So in the range. So you're looking at 2 plus some multiple of 2 to the third, right? In this sequence, and that's got to be, I guess, the first one of these, or yeah. Excuse me. And this is looking like 2 to the third times some. I guess what I want to say is, if the number was larger, there might be yet another routine here. So okay, so let's say you get 614, and the next thing that happens is you remove, like you could have 614, if you add 8 to this, 22. Whoops. That would be like n equals 22. Then you might actually do, you might lose 6. Excuse me. You might lose 6, end up with 14. And what would this sequence look like? This would be 2 plus 2 to the 4th j. I think so. This sequence is not 2 plus 2. This is not actually. This is actually 2 to the 3rd j minus 2, right? Is this sequence, or it's this sequence, right? No. Yeah, it's this sequence. And this sequence is what? 2 to the squared j minus 2. Right? 4 minus 2, 8 minus 2. Yeah. Interesting. Excuse me. And then finally this sequence, 6, 14, 22, this is 2 to the 4th times j minus 2. And if it were over here, 8, 16, 24, that would give you 16, right? 8, 24. This looks like 2 to the 4th j. So really, now the question is, n is 22 here, and n is 24 here. But again, we're just looking for patterns here, something that we can kind of understand, grasp. Again, we're already 30 minutes in here, kind of analyzing things. What's interesting is this is 16 minus 2 is 14. 32 minus 2 equals 30 is greater than 22. However, if we were looking at, what was this number over here that we had 14? If we had something less than 22, like if we had 21, we wouldn't get 14 here. We'd actually get 6. And it's 21. 16 minus 2 is 14. 14 exists. It's not, somehow doesn't make the cut. And I guess that's a question. Like, how do we know if it's 6 or 14? Right? Like, how do we know? It's clear like what these sequences are going to look like. But I guess what I mean is, this one doesn't make it that far. This is 2 to the 3rd j minus 2. We don't get to 2 to the 4th j minus 2. Right? We're not big enough from 21. This one's only here, which is 6. Whereas this one is here. Now, why might that be? That's an interesting question. I think that has to do with n. It's n, a logarithm of n. I want to say that's what it is. If you take log base 2 of 21, right? So like 2 cubed is 8, 2 to the 4th is 16, 2 to the 5th is 32. I want to say it's somehow related, but I don't think it is. It doesn't. It's not obvious how it's related. 14, huh? I want to say it's going to be. It's not obvious at all, right? Because 21 and 22 are like right next to each other, and they don't seem to break across either of these bounds. If that makes sense. Well, one of them is even, one of them is odd. So I think it's not. It's comparing apples and oranges, right? It shouldn't be 21 and 22. It should be like 22 and 20. 20, it looks like. Well, 20 might actually have. No, yeah, 20 would not have 14. 21 is actually totally different from 22, but 20 would not have 14. And that's not obvious to me at all. Why 20 would not work here. If you add 8 to 14, that's greater than 20. And therein lies the problem. You've got to be less than or equal to n for that to exist here. I think it's actually 2 raised to the third j minus 2 equals 22. It's got to be less than or equal to n. Right? So 2 raised to the 3j less than or equal to n plus 2. J less than or equal to n plus 2 over 2 raised to the third. That is to say, you have 20 plus 2 over 8 equals 22 over 8. Right, that does seem to make sense then. That's less than 3. Uh-huh. It's actually... Yeah. See, that's kind of the deal. We want this to be exactly 2. Right? Or rather, not exactly 2, but where this ends is when this 2 raised to the... So there's... This is a little weird, but... Alright. There's 2 raised to the k j minus 2, right? Is less than or equal to n. So we want to know what k is, right? So n plus 2, 2 raised to the k. And what we're trying to say is that there's going to be a point where j is just 1, right? That's where we're ending, when j is 1. So we have 14 here because this is 2 to this k is right. So we let j equal 1. This figures out, now we can figure out what k is. So k is less than or equal to log base 2 of n plus 2. Right? I think that makes sense. So, excuse me. And k is an integer. So that means positive integer, right? Non-zero. So that means if n is let's say, so this is for even numbers, right? So when we're even, that's when we get this kind of setup. When we're odd, it's different. But we can say we're even. Let n be like 18, 19, 18, 20, and 22. 22 and 24. That implies that k is got to be log base 2 of 20. which is 4. It's gotta be less than that. Log base 2 of, I think it's also -1 somewhere in there, by the way. 20, so 22, so wait, 20 log of 24 log of 22 it's 4.5, still 4. Basically, you take the floor. Okay. Excuse me. Coughing in the mic. It's great. 22 plus 4. Excuse me. 22 plus 2. Right. And then log base 2 is still 4. And finally, 24 plus 2 still 4. Okay, that didn't seem to change much. That doesn't seem right. Why is this wrong? What is wrong here? Now we're basically, I don't know, I'm so confused. Oh boy, what did I do? What is K when we're looking at 16? Actually, these might be correct. Might be. What I don't think I should have calculated these. So these are basically these are all 16. So these end up being 14. All of these. But that's wrong, I think, right? 18. We end up with 2 to 18. Then we end up with half of those. 2, 6, 10, 14, 18, I want to say, right? We get rid of 4, skip 6, 8, 12, 16, yeah. Then we go right to left, and we get 2, 1, 2, no, we get 6 and 14. Oh no, all right. That is 14, yeah. Am I crazy? All right, I think that means that we just take if n modulo 2 is 0, then 2 raised to this thing minus 2. Floor of log base 2 of n plus 2 minus 2. Otherwise, floor of log base 2 of n. All right, the other one is, excuse me, the other one is actually just a, it's like the same thing. 2 raised to the k is less than or equal to n. And so that means that k is just log base 2 of n. Which then gives you, whoops. And it's also 2 raised to the kj. It's the first value in that sequence, which is just 2 raised to the k, which is really just which is interesting also. Is that right? Like 8. What's 8? I don't know, not 8. 9. Yeah, 9. 9 log base 2 of 9 is, like, floor of that is 3, I think. Right? Yeah. Yes. And then 2 raised to the third is 8. Which is not 6. Wait, what? What? What happened? Wait a minute. It's not even. We get. Wait a minute. What? Oh no, because. All right, hold on. What happened? Definitely just wrong. I don't know. Only even numbers. And then from right to left, skip numbers, and then 6. Why did I think it was going to be? When you get rid of the even numbers left to right, you're left with 2, 4, 6, 8. When if you do the same thing on 1, 2, 3, 4, 5, 6, 8, get rid of the even numbers or the odd numbers, you're left with the same thing. Yeah. So actually, these are equivalent. These should give you the same exact answer, which is, yeah. So it doesn't matter if it's odd or even. It's just exactly what we had here. 2 raised to the floor of log of n plus 2 minus 2, which is so weird, by the way. So we do log base 2 of 11 floor. That's, I think, 3. That's 6. Yeah, all right, let's give that a shot. All right, let's go for it. Let's go for it. Standard log 2 of n plus 2 floor. Let me just int. And then take the power of 2 of that, also an integer, and then subtract 2. What do you get? One, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. Some numbers in between. Excuse me. All right, how do we do? Wrong. Really? A whole bunch of these are wrong. Wow. Okay. Totally wrong. Nice. Yeah. What? What do you mean? Okay. Let's try one of the smaller ones. Let's try like 223. Gulp. Why is my input not, Oh wait, did I not? I did that. Thought that I did that. 223, 126, 96. Okay, so we have 223. So this was just wrong. We're gonna get rid of all that, by the way. So we have more space. 1, 2, 2, 3. First execution, we get 2, 4, 6 to 2, 2, 2. Then we get to from right to left. 2, 2, 2, 2, 2, 0, right? 218. Now the question is, do we end up with 2 at the end or 4 at the end? What did I do here? 2, 2, 2. 220. What am I doing? 2, 2, 2. Okay, how many of these numbers are there, right? There are 111 of those, right? If we divide by 2, it's 1 to 111, so it's 111 of these. It's an odd number, which means what? Which means you're going to get rid of starting from the right, every other number. If there were 3 numbers, 1, 2, 3, it would be you would have this number, right? So you're gonna have 4 here. I'm sorry, it does matter if I do. It does matter if it's odd or even, I guess. I think, I don't know, I'm confused. So never mind, I was wrong. This is the wrong. I want to say it matters. I want to say something like you actually want to take n and you want to divide by, like you want to find out, basically convert it to base 2, and then that gives you some information about it, like what's going to be left over after each iteration. So yeah, so we have 223 numbers. Whoops. And then we divide by 2, we have 111 numbers, right? There's a remainder of 1. 111 numbers. Divide that by 2 again, you get 55 numbers, right? Rounded down. And these are going to start with 4 because we got rid of 2 over here. So it could either start with 2 or 4. So that's the thing. If it was 224 numbers, or 224 over here, 224, and then divide by 2, we get 222 numbers because we'd have 224 over here. Then we wouldn't actually eliminate 4. We'd eliminate 4. We'd have 2 on this side left at the end, which is significant, right? That's very, very significant. Have 56 numbers. Then we divide by 2 again. We get 26. Sorry, excuse me. Just laughing at the idea of something that was kind of thought crossed my mind. It was really ridiculous, and I don't know, maybe laugh. Sorry, excuse me. It's really stupid, but struck me. Hopefully not. I don't think so. Hopefully, just thinking about it. So yeah, hopefully not. I don't know. Do a lot of weird, strange things. Sometimes they my mind things play out in a certain way, and it's like that won't happen. Don't worry about that. It's like, don't be ridiculous. Okay. 55, 26, 13. So what we end up with 4, and we have 55 numbers, right? No. So this corresponds here. This is here. This is here, right? Starting with 4. Because we have this remainder 1, that'll basically tell us whether or not I think we remove, yeah, either, So basically you have a choice between these two numbers to be the first part after the execution. And I want to say, because this is odd, you're going to end up with this one. If this were even, you would end up with this one. Yeah, I think that makes sense. So depending on the remainder of this, right, you'll have either one of these two. And then same thing on the left side. Well, the left side, so this is every other removal matters. So this one you're gonna go left to right, right? So you're certainly gonna get rid of 4. You're gonna end up with 8. So it's gonna be 4, 8 is left, 12 is gone, 16, ... all the way up to. Now see, I don't know what number is left. Well, it's 26 of them, right? So 26 times 8 really would be it. 26 times 8. It should be 208. And we would have removed 204, 212. Why wouldn't we have? Why in the? Oh, this is 27. I'm sorry, that's wrong. 216. Yeah, we would have removed. There, 224 doesn't even exist here, and then 220 would be removed, right? So now we're at 8. That's kind of interesting. And then now we have a choice between these two numbers when we go down to 13 numbers. And the choice we make is, since there's an odd number here, right, if it was odd or it's even, it would be a different choice here. But since it's odd, I think that's the question, is odd means the second one gets chosen. Yeah, because you do 3 numbers and 2 numbers, right? If it was 2 numbers, it'd be the first one. Or if it's 4 numbers and 3 numbers, right? So like 1, 2, 3, 4, and 1, 2, 3. From the right, it's the second number. From the right, it's the first number. It's going to be the first of the sequence. Eventually, basically, we're going to have the first of the sequence is the number that we're interested in, right? So that's why we're paying attention to what gets removed. So every other sequence, we want to know what gets removed. And so from 27, we end up with 16, right? So 16 is going to be the next, and there's 13 of those, so it's going to be 16 times 13, right? It's actually not too bad to think about. It's a really interesting question. It would take me forever to get here, though. So 208, so we lose 216. How long has this been? It's been over an hour. Yeah. I mean, I don't think, like, I'm not that smart, you know. Like, I don't think I could have solved this in a short period of time. I don't think so. And then now, so we have 13 numbers, right? And now, is it every time? Now from left to right, excuse me, now we have 6 numbers, and of course it's 32 times 6, whatever that is. Just 192. Don't really care that much. Right, obviously we always remove the first one from left to right. And then if this is odd or even, so this is even, so now this time, even, we select the first number of these two, right? So if 64 is here, we would select the first of them. So now we have 32. As we go down to 3 numbers, it's 32, skip 64. So we have the 6 numbers is sort of 32 times 6, which is, right, 192. 64, 96, so on to 192. Now we only have 3 numbers. We have 32, 96, and 96 plus 64. It's 160. Right? That's really interesting. The reason, now that's kind of a meaningful thing there. this kind of gets into like where my other ideas kind of start to fail. And we have 3 numbers, and we said we always, from left to right, we always just pick the next one, right? So we have 96, 1 number, done. Now the question is, like there are a few questions here. So the sequence is going to be, in some cases, it's like, I guess we don't need to keep all of the other numbers. We only need to keep like the first number and know what the next number is going to be. The first 2 numbers are only really 2 numbers we care about at each step. So always the first iteration, we know what's going to happen. We're going to get the next number of the sequence. So we kind of need to know that at each point, like what that's going to be. And then we always need to know what the first 2 numbers are going to be, no matter where we are. And then we only care on every other jump, if it's odd or even, the number we're jumping from, then we're going to select either the first number in the sequence or the second number in the sequence. And to generate the number from there, it's a power of 2 away each time, right? So some power of 2 that we increase. So like for 16, the next number in the sequence is 32. When we jump to 32, the next number in the sequence is just double that, right? So it's a lot of the time it's just double that, but sometimes it's not just doubling that. It's sometimes, like if the sequence was 2 and 6, right? It's, you have to add that power of 2. Yeah, so I don't know. I'm not exactly sure how to describe. I think I have an idea of what this algorithm is and what it looks like, and yeah, we could do it in logarithmic time. However, I'm still not really clear on like exactly how to do that, the details. Yeah, so let's try with another example. Like let's do one of the ones we were looking at before. It's like 19, 1 to 19. We would say, okay, we're definitely going to have 2 initially. And that'll get us to 19. We're gonna get, yeah, that'll get us to 18. And we said divided by 2 is 9, right? Floor. Now we're gonna. This is significant from the right. We know these are the first 2 numbers are 2 and 4. We just kind of happen to know that, I guess. Because it's odd, we're gonna select 4, and now we're saying 4, 8, 16. And really those are all the numbers, because when we divide by 2 we get 4. Oh, excuse me, it's not 4, 8, it's 4, 8, 12, 16. And there's 4 numbers. And then we always remove the left one. So we have 8 and 16. And that's 2. And then we have a choice. It's going to be the first one. 8. Okay. Right, so the even gives us the first element. So odd would give us the second element. So it's actually going to be, there's a power of 2 in each the difference between each of these values in this first step is 1, right? 1, 2, 3, etc. The difference in this sequence is going to be 2. The difference in this sequence is 3, or excuse me, is 4, right? 4, 8, 12. And the difference between the values in this sequence is 8. That's like the key. So at each step, there's some power that's going to be like the sequence difference. So you could just add to generate. You always know what the first number is going to be because you select it from the previous step, and then you can always know what the difference, how much you have to add to that value to get the next number, right? Because that increases as you step as well. And so you can use that to generate. If you need the first 2 numbers, you can generate the second number using that. So if we went back to 223, that other example, right? We said 1, 2, 2, 3. So we're trying to like formalize the algorithm a little bit more here so we can actually code it. So 2 to 0 is the step. Now we go to 1, 1, 1. This is we always pick the second on the first step, and then the next step we have a choice. So now I have 2, right? The difference in sequence is 2, 4, we only really care about the first two elements also. So of 1 and 2, we would pick 2. Now 2 4th step, we can generate 4 using 2, right? And now we have a selection. So this is odd. We said if it's odd, we pick the second number. And we said the step is now 4. So we have these two numbers, 4 and 8, to pick from. This is now 55. We said every other step we don't pick. We just always pick the second one, right? So 8. So now we have 8. To generate the next number, we add 8, 16. We have 26, or 27 rather. Here we have a choice to make. So we pick the second one. Our next step is 16, 16 and 32. This is starting to become a little more algorithmic, or formulaic. 13, or simple. Yes, you can kind of see the steps. 13, we say we don't. Every other point we don't select. We always just pick the second one. So 32 again. The step now is 2 to the 5th, which is 32. We have 64. Oops. And 7. Now we have a choice. Oh no, excuse me, 6. Now we have a choice. It's even. We would pick the first one when it's even. So now we have 32, and 2 to the 6th is 64, which gives us 96. 3. We always pick the second one, I think, on the ones that there's no choice, right? Every other time we always pick the second. So we pick 96. 96. Step is 2 to the 7th to generate the second number, and we only have one number. When we have one number left, then we're done. We don't have to select the second number. So that's the algorithm. Not too bad. Somewhat complicated, but not too bad. So we have a step. We have n. It's going to be kind of n. We say, and we have two numbers that we sort of generate using the step, and select, depending on n, we select the next number in the sequence. And that eventually will give us what we're after. Something like that. Let's try to code it. Step will start off at 2. I'm going to say while n is not equal to 1. Really, it's not equal to 1. We're going to say at each, it's really a for loop even. Could really do a for loop. Use t. T is greater than 1. We're going to bit shift t to the right 1. Divide t by 1 at each step. And we're also going to have a toggle. Yeah. True. We'll start with true. So, yeah, I don't know. This is going to handle like the swapping back and forth between choosing and not choosing. So t, bit shift to the 1 after each check. And we also toggle, I think, also. And we increase the step. Step, we bit shift to the right once, and toggle, we set to not toggle. Right, that's sort of what we do at each step for the next iteration. We say if toggle. So the first thing we do, yeah, we could say false or true initially. So if toggle, then we immediately pick the second element, and then we actually have a current element start off at 1. Right? So we have two elements, and we can even put them into an array. Well, we don't really need to do that. So we could generate the second one as needed, right? So if toggle, then we're always going to do current equals plus equals step, right? And initially, actually, step should be 1. So initially step is 1, current is 1, toggle is true, plus equals the step. And otherwise, now we have a choice between if we're not toggling, now we have it's t modulo 2 equals 0, or it's equal to 1, right? We'll keep it kind of simple and we'll just do that. We could also do and 1, that's another way of doing this. And 1 means it's, so if it's equal to 0, and you could just do, if this is odd or even, right? You could do it this way. So if this is odd, we said if it's odd, we pick the second one, current plus equal step. If it's even, however, we actually pick the first one. It's kind of interesting. So the step still increases, but current doesn't change. And in that case, we say, we can just do else if t and 1. Try to figure out this algorithm from from the code. This is like, oh man. And I think it works too, by the way. I think it works. Oops. It's quite the routine we got going on here. I don't know. Well, I don't know if it works. Oh, it does. Yeah, there you go. Hey, check me out. Are you kidding? Let's go for it. Let's go for it. Wait, how? Yeah, let's go for it. Hey! Oh, no kidding. Ah, it's too funny. Quick maths. Quick maths. I love these problems, man. They're so much fun. So satisfying when you get them. That was like over an hour and 10 minutes, 12 minutes. It's quite a bit of time we spent on this. But yeah, we got there. Careful analysis of I guess what happens at each step. Again, there's only a logarithmic number of steps, so you can kind of somewhat simulate what happens. And again, we only really care about the first two elements. So pretty interesting problem. Like this is kind of why I think you could write machine learning algorithms that can solve certain problems, because even though this was like technically, like an algorithm that we found, we really did this by just looking at the data. This is kind of a very raw data approach to problem solving, where we were just like, well, what information do we really need to keep track of to kind of compute these to try to compute these numbers? And as it turns out, not too much, right? Like this, like we could do this very efficiently, I guess. And it feels like there really wasn't really very much. It feels like there really wasn't that much logic involved here, as much as it was. It just kind of noticed some things. Yeah. Or it's interesting. You could also do or t and 1, right? Does that work too? I think it's the same thing. Hey, yeah, same deal. Yeah. There's probably a more efficient way to do this too, by the way. Quite possibly. Because I'm noticing the memory usage for some people, it's lower. Somehow I ended up using more memory. But yeah, look at that. Look how beautiful that is. This is like just a few lines of code. That's awesome. That's awesome. You don't even need the math library either. You don't need that. You don't need that. Don't need none of it. Wow. Alright. That's just satisfying. Oh no! We got 4 milliseconds this time. Oh, there we go. Oh, it uses less memory because we don't load the library. That's funny. Nice. Can we get rid of the toggle and the step and all that? Maybe. I don't know. I'm trying to use less memory, right? Nah, that's probably fine where it is. Yeah. Anyway, yeah, let me go. So yeah, thank you for watching. I will talk to you soon. I think I'm going to take a break. Probably go exercise. Exercise, take a shower. Yeah, exercise, take a shower, get food, and then cozy up with the Bible for a bit. Exercise, take a shower, get food, cozy up with the Bible. Probably in between both of those things. Probably will. I don't want to eat while I'm reading the Bible. I don't want to get grease all over my Bible, or the Bible. But I do want to exercise when I'm drying off after my shower. That's when I read the Bible. I think that's a good time to do it. Exercise, eat, or exercise, shower, read the Bible, eat, read more of the Bible. I don't know. Probably. I might come back and do a few more problems, like maybe another problem or two before I go to bed. I have to kind of decide, but yeah, let me go. Thank you again for watching, and talk to you soon. Take care.